The equation of a curve is y equals 2 over x minus 3. We want to write down the equations of the asymptotes and sketch the curve. Now, this kind of a function is known as a rational function. It's a ratio of two expressions, one expression over another. We can think it comes from rational numbers actually. A rational number is a number of the form a over b, where both a and b are integers. So that's probably where the name rational function comes from. Now this function is not defined at x equals 3. So for this function x cannot equal 3, because if it did, we'd have 2 divided by 3 minus 3, which is 2 divided by 0, and this is undefined. Okay, we cannot divide a number by 0, because if we did, then whatever the answer would be, if we multiply it by 0, we get 2. So for example, if 2 divided by 0 equaled, say, a, that means that a multiplied by 0 equals 2. But of course, any number multiplied by 0 is 0, so this can't be true. So x cannot equal 3, so that means that at x equals 3 we have a break in this function. This function is defined everywhere except at x equals 3. So if we were to look at a graph, then at x equals 3 we have no value of our function. So what we do is we just put a dotted line at x equals 3, indicating that whatever the graph looks like, it cannot cross this line, because if it did cross the line, then we'd have a value at x equals 3. So this vertical dotted line, known as a vertical asymptote, is a break in our function. So there's a break or discontinuity at x equals 3. So the graph of the function cannot cross this line. So basically, to find our what's called our vertical asymptote, we just set the denominator equal to 0. So we put the denominator of our rational function equal to 0. So for this particular function, the denominator is x minus 3. So by putting x minus 3 equal to 0, we get x equals 3. So this is the equation of our vertical asymptote. So the equation of a vertical line has a simple form. It's just x equals a constant. That constant is the number that our vertical line passes through on the x-axis. So for example, x equals minus 1 would pass through the point minus 1. X equals 0 would pass through the point 0. With x equals 0 is actually the y-axis. So a vertical line has a very simple form. A y term does not appear in it. All the points on the vertical line have x values of 3. That's all we need. X equals 3 fully specifies this vertical line. Now for rational functions, we also have what's called a horizontal asymptote. That arises from taking the limit of this function as x tends towards infinity. Well, x could approach infinity, plus or minus infinity. So for very large positive values of x, our function will approach 2 over infinity. Well, infinity minus 3 is essentially infinity, so we're going to have 2 over infinity if you like. This is an abusive notation. Infinity is not actually a number, but this is essentially 0. So as x approaches infinity, our function will approach 0, but will never actually get to 0. Similarly, if x, for very large negative values of x, as x approaches minus infinity, it doesn't matter whether we have 2 divided by plus infinity or minus infinity. Well, it's actually minus infinity minus 3, but of course that's the same as infinity. As x approaches either plus or minus infinity, y, which is our function, will approach 0. So that means our graph will approach the x-axis, because on the x-axis, points on the x-axis have y equal to 0. So the equation of our horizontal asymptote is got by putting y equal to this number here. So this is the equation of our horizontal asymptote. Y equals 0 is just the x-axis. So for very large values of x, large positive or negative, our graph will get closer and closer to the x-axis. In other words, the y values of the points will approach 0. Now, we want to sketch the graph. Rational functions come in two sections, and this vertical asymptote divides the curve into two sections. Well, actually, both asymptotes, both vertical and horizontal asymptotes, will divide our function. Well, it'll divide the plane into four regions, four quadrants, 1, 2, 3, and 4, and our function will be in two of those quadrants. And it will be in the two quadrants that are images of each other under central symmetry in the intersection of the two asymptotes. So one section might be up here, for example. It'll actually be in the shape of what's called a hyperbola. It will look like this. And the other section will be got by mapping this section through this point. So the other part will look like this. It'll have exactly the same shape as this, got by central symmetry in this point here. So a rational function has the shape of a hyperbola, and for example, if it was up here, the end of this curve will approach this vertical asymptote but never cross it. So you'd often indicate it by putting an arrow on it, which means that the curve gets closer and closer to this vertical line but never crosses. Similarly, our curve gets closer and closer to our horizontal asymptote but never crosses it. So we put an arrow here indicating that. And if one section is up here, then the other section is here. So for this particular curve, y equals 2 over x minus 3, we have to decide, is it like this, or is it in the other two quadrants? So what we want to do now is graph this. So just get one point on it first. So for example, you could let x equal 0. That's one way to plot one point. So just replacing x with 0, we get minus 2/3. So the point 0 minus 2/3 is on the curve. So that tells us that one section of the curve is in this quadrant here. So this is the point with coordinate 0 minus 2/3. So one section is here. And actually that's not very well drawn. This end here approaches our x-axis. So this is one section, so that means the other section is up in this quadrant. So to find this other section, we just map this section here under central symmetry in this point. So for example, if we were to take this point here, we just map it through and go out equal distances on either side of this point, and we get this point here. Okay, it's not the best sketch in the world, but it's close enough to what it looks like. So both of these sections should have the same shape. If you want to graph it, you can go to wolframalpha.com and type in y equals 2 over x minus 3. You need to bracket x minus 3, hit return, and you get a graph here, and the vertical asymptote is at x equals 3. So both sections of the graph have identical shapes. So this is a better picture than what I drew. So what's the meaning of this vertical asymptote? Well, as we approach 3 on our x-axis, our graph blows off to either plus infinity or minus infinity. So, for example, if we were to take a value just to the right or just greater than 3, suppose we took this value here, x equals 3.01. And if we plug that value into our function, we'll get y equals 2 divided by 3.01 minus 3. But that's just 2 divided by 0.01. That's 2 divided by 1 over 100, if you like. So that's 2 times 100, which is 200. So at x equals 3.01, we get a y value of plus 200. Okay, so that's a very large positive value. And if we were to take, say, instead of 3.01, 3.001, which is even closer to 3, so we're approaching x equals 3 from the right, then we'd have 3.001 here minus 3, that's 0.001. That would give us an answer of plus 2000. So you can see that as we get closer and closer to x equals 3 from the right, our value of y approaches plus infinity. So we could write this as x approaches 3, and we could put a plus sign here to indicating we're approaching 3 from the right. Y tends to plus infinity. You can consider approaching x from the left. So if we take a value just to the left of 3, or just smaller than 3, suppose we take the value 2.99. So if we have x equals 2.99, y will equal 2 divided by 2.99 minus 3. Well, that's 2 divided by minus 0.01. That's equal to minus 200. So when x equals 2.99, we're getting a large negative value. We're getting minus 200. And you can imagine going even close, approaching 3 more closely from the left. Say we had 2.999. Then y would equal 2.999 minus 3, or minus 0.001. So we get an answer of minus 2000. So what this means is that as x approaches 3 from the left, actually the minus sign will be written here. So up here we would have x plus, whereas down here we have x minus. So this indicates we're approaching 3 from the left. We can see that y would tend towards minus infinity. We could also look at what happens as x tends towards infinity. Suppose we let x equal a very large value, say plus 100. Then y will equal 2 divided by 100 minus 3. That's 2 divided by 97. Okay, so that's a very small positive number. So if we take x equals plus 100, it's way out here on the positive x-axis. So remember, our function approaches our x-axis but never crosses it. So we get a very small positive number. If we change 100, say, to 1000, which is way over further, I haven't drawn this to scale, but I think you get the idea. If we replace x with plus 1000, then we'll have 2 divided by 1000 minus 3, which is 2 over 997, plus 2 over 997. That's a much smaller positive number. So you can see what's happening. This number here is approaching 0. So as x tends towards plus infinity, y is tending towards 0. And it's the same story for this section of our graph. As x approaches negative infinity, say we have minus 1000, what we will get is, well, we'll essentially get this same value that we got here, but we're going to get minus 2 over 997. Okay, so I explained this at the start, but now I'm just showing you with some numbers, actual numbers. So as x tends towards minus infinity, y will tend to 0 as well. So if we had minus 1000 like we have here, we'd get 2 divided by, well, actually, I said that the value we get is the negative of this value. That's not true. We'll have 2 divided by minus 1000 minus 3. So this will be 2 divided by minus 1003. Okay, what I said earlier wasn't strictly true, but it doesn't matter. The general idea is that this number here is approaching 0, but approaching 0 from below. Okay, so that's why we have an arrow on our graph. So our graph is approaching the x-axis, but never actually crosses it. This section of the graph gets closer and closer to the x-axis. We want to prove that no two tangents to the curve are perpendicular to each other. Okay, let's look at two tangents to this curve. Well, it's not one continuous curve. It's actually the function is made up of two curves. It's discontinuity at x equals 3. So let's look at any two tangents. So we could pick a tangent here at this point. And we could pick a tangent at another point, either on this section, we could pick a point here and get a tangent, or we could pick a point here, get a tangent. even just without doing any calculation, what's noticeable about all of these tangents? Well, all of them have negative slope. The slope of all of them is less than 0. How do we know that? Well, because the tangents are going in this direction. Even, if we take a point here, we have a line that's almost horizontal, a tangent that's almost horizontal, but it still has negative slope. It's still sloping downwards. In other words, if we pick any point on it, increase x by 1, y is decreasing. The actual slope would be got by picking any point on the tangent, increasing x by 1, and then we'd find that y actually decreases. Okay, so all of these tangents are sloping down as x increases. For increasing x, y decreases for any point on these tangents, whether we're on this section or the other section. It doesn't matter. So you can see that from the graph straight away, that all tangents have negative slopes. So even without doing calculations, we can see that. You might say, what about the tangents down here, say at this point here? Well, that's almost a vertical line, but it still has negative slope. Similarly for tangent here. Okay, actually what's happening is, as our function, our curve approaches x equals 3, the vertical asymptote, our tangents, the slope of our tangents is approaching infinity. So the tangents are approaching this vertical line as well, actually. But they all have negative slope on the way to that infinity. All the tangents have negative slope. They're sloping downwards. Now, since all the tangents, all the slopes have the same sign, they're all negative, that means that no two of them can be perpendicular. Because for a condition for two lines to be perpendicular is that one slope is positive and the other slope is negative. So, for example, suppose we take these two lines here, perpendicular lines. Well, the blue line has a positive slope. We'll call it M1. The slope of the blue line is M1. But our other line, which we'll say has slope M2, is negative. That's a fact for perpendicular lines. So that's not happening here. All the slopes are negative. Okay? You might remember that, say, if one slope, say the blue line has slope of, let's say, plus 2/3, it has to be positive. It's going this way. In other words, if we pick any point on it, increase x by 1, then y will actually increase. So the slope is positive. Then M2, the slope of M2 is got by inverting plus 2/3 and changing the sign. So the slope of M2 will be minus 3/2. Okay, I explained why that is true in an earlier video. I explained the geometry of this setup. So yeah, that's a kind of a proof. Well, in an exam it mightn't give you full marks, but I think it should give you close to full marks. Now I just want to go through a more precise proof involving getting the derivative of this function, because the slope of a tangent to this function is the derivative. So if you go back to differentiation from first principles, you learned that the slope of tangents to any function, this function here, this graph, at x, so x is any value on the x-axis. So, we could take this value here for x. So the slope of the tangent at x, if we go up to the curve and construct a tangent, then the slope of this tangent here, that's the line that touches the curve at just this one point, is dy dx. So what I'm going to do is calculate dy dx for this. By the way, it's easy to remember that the slope of a tangent to y equals whatever is dy dx, because this should be reminiscent of y2 minus y1 over x2 minus x1. When we have 2 points on a line, we get the slope using this formula. So you can see it's y over x, but here we're dealing with a limiting case. y2 minus y1 becomes dy, x2 minus x1 becomes dx. So I won't go through differentiation from first principles, that's in another video. I'll just go ahead and differentiate this function. So I could use the quotient rule to differentiate this function, but what I'm going to do is write it like this. Our function can be written as 2 times x minus 3 to the power of minus 1, because the denominator is to the power of 1, so what I can do is bring it up. Instead of 2 divided by x minus 3 to the 1, I can write it as 2 multiplied by x minus 3 to the minus 1. So when I'm differentiating this, I can use the chain rule. So this is a good idea if the numerator is just a constant. If the numerator doesn't involve x, it's probably quicker to apply the chain rule. Write your function like this, and using the chain rule, we just deal with the power of the brackets first. Multiply minus 1 by 2 to get minus 2. Subtract 1 from this power. Minus 1 is minus 2. And then multiply by the derivative of what's inside the brackets. So if you differentiate x minus 3 with respect to x, we just get 1. And we can write this as minus 2 over x minus 3 all squared. So x minus 3 to the power of minus 2 is just 1 over x minus 3 squared. So this is the slope of a tangent to our graph at any point x. But we can actually see that this quantity is negative no matter what x is, because the term on top is negative. Minus 2 is certainly negative. But what's underneath, that is our denominator, is always positive. Because no matter what x is, no matter what value we take for x, when we work out x minus 3 and square it, we get something positive. Because when we square something, it's always positive. So we have a negative quantity, minus 2, divided by this positive quantity. So that means negative over a positive is always negative. So dy dx itself, this entire thing here is negative for all x. So that proves that's a more mathematical proof that the slopes of the tangents to this curve are always negative for all values of x. So that means that no two tangents can be perpendicular, because for two tangents to be perpendicular, well, one tangent has to have negative slope and the other tangent has to have positive slope, and that's not happening. Just to reiterate, for two tangents to be perpendicular, their slopes must have opposite sign. All tangents to y equals 2x minus 3 have negative slopes.